To build a neural network from scratch, you have to take raw data and string it together into a structured, connected digital web. If you've been following along, you've already mastered the foundational pieces of PyTorch, tensors, autograd, and the nn.Module. Today, we're taking those standalone pieces and connecting them into one complete, functional artificial neural network pipeline. Looking at our terminal here, we can see our pipeline is initializing and the status is ready. Let's get to work. Connecting these PyTorch functions transforms isolated math operations into a structured architecture for image classification. First, we set up our environment with standard libraries like pandas and PyTorch and set our manual seed to 42 for reproducible results. Right below that, we use pandas to read our CSV file, loading our Fashion MNIST dataset into a data frame. This terminal output shows our raw tabular structure. The first column holds our target label, the actual clothing category, while the remaining 784 columns contain the individual pixel values. To make sense of these pixels visually, we need to restructure them. By calling reshape, we take that flat row of 784 pixels and fold it back into a two-dimensional 28 by 28 grid. Now we can see what the neural network will actually look at. We have a clear grid of clothing items, each correctly mapped to its corresponding numerical label. Visualizing the dataset is a required first step. You must understand the shape and boundaries of your data before feeding it into a rigid algorithm. Next is pre-processing. We separate the dataset into training and testing sets to independently evaluate performance later. Then we normalize the raw pixel values, which range up to 255, by dividing both sets by 255, so our model can effectively learn the weights. Looking at this array output, we can verify that the scaling worked. All of our pixel values are now compressed between 0 and 1. Now we need to package this data for PyTorch. We do this by building a custom dataset class that converts our raw NumPy arrays into floating-point PyTorch tensors. And here is the raw tensor output for our very first training item, confirming the conversion was completely successful. If we skipped this precise normalization and tensor conversion, the network's gradients would explode almost immediately, causing the entire training process to fail on the very first pass. We configure data loaders to feed shuffled tensors in batches of 32. Then we define the network architecture, funneling 784 input pixels through hidden layers of 128 and 64 nodes out to 10 target classes. Finally, we set our optimizer and training rules. Based on our dataset size and batch configuration, the terminal confirms that our model will process exactly 150 batches for every single epoch. This specific sequence of nodes dictates the physical architecture of the model. Meanwhile, hyperparameters like the learning rate and optimizer dictate exactly how aggressively the model learns from its mistakes. Now we enter the training loop. We start with the forward pass, where the model predicts on batch features and calculates loss. Then comes backpropagation. We clear old gradients, calculate new ones backward, and step the optimizer to update weights. When we check the terminal logs, we see the model is successfully learning. Across these early epochs, the calculated loss drops steadily from 1.32 down to 0.52. Plotting this out as a line graph gives us a clear visual of that downward trajectory. We can watch the error rate compress as the model converges toward accuracy over the full 100 epochs. With training complete, we have to switch the model into evaluation mode. By wrapping our test code in torch.nograd, we disable gradient tracking, preventing the model from updating its weights while reviewing the test data. This repetitive loop, guessing, measuring the error, and adjusting mathematically, is the absolute core of how artificial intelligence is generated. Finally, the terminal outputs a clear summary of our sequential architecture, followed by an exit code of 0. The code executed perfectly from start to finish. We just built a pipeline that ingests a stat file of raw pixel data, normalizes it, and trains a structured PyTorch algorithm to accurately classify images. If this breakdown helped you understand the mechanics of deep learning, make sure to subscribe so you don't miss our next programming tutorial. Mastering these core building blocks provides the foundation required to develop and refine more complex neural networks in the PyTorch ecosystem.